Section 21, Structure, Galaxies, Filaments, Cosmic Voids. This video was updated February 2025. 84% of the matter in the universe is cold dark matter, and 16% is ordinary baryonic matter. Cold dark matter is believed to not interact with electromagnetic radiation and ordinary matter, except via gravitation, at least after 1 second after the Big Bang. After a couple decades, there were slight overdensities and underdensities of dark matter at all scales. Slight overdensities of dark matter expanded slightly more slowly than the universe's average expansion, a relative contraction, and slight underdensities expanded slightly faster. The relative contraction rate of slight overdensities of dark matter increased once matter-dominated expansion after 50,000 years, even while ordinary matter was still a hot plasma. The smallest size overdensity regions will later become the dark matter halos of galaxies and galaxy clusters. Whatever constitutes dark matter, it is believed to attract itself only gravitationally. Unlike ordinary matter, dark matter seems to have no way to turn its kinetic energy into radiated heat. It seems collisionless, or its collisions are elastic. Eventually, the smallest size dark matter overdensities contracted enough to become gravitationally bound, but did not collapse to a point or to the density of a star. Dark matter formed the large diffuse halos within and surrounding present galaxies. The smallest size dark matter underdensities expanded and became cosmic voids. Cosmologists believe that galaxies with stars within dark matter halos formed and became gravitationally bound before clusters of galaxies formed and became gravitationally bound. Smaller size before larger size. Cosmologists call this structure formation. In particular, a bottom-up formation of structure. However, galaxy superclusters coalesced late enough to not be gravitationally bound, with expansion now accelerating. The James Webb Space Telescope sees early bright galaxies that the Hubble telescope could not see. Cosmologists may refine their theories of structure formation based on new data, so those chapters from existing books may need to be revised. A good question is whether the average energy density of our region of the universe on scales larger than 200 megaparsecs equals the average energy density of the entire universe, or is slightly higher or slightly lower. The standard cosmological model assumed that our vantage point is representative of the entire universe. Here are some of the superclusters and cosmic voids in our neighborhood. The cosmic voids are relatively devoid of galaxies, but still contain diffuse ionized hydrogen and helium at slightly lower density than the universe as a whole. I have not found any reference to the density of dark matter in cosmic voids. The universe is only homogeneous on a large enough scale, 200 megaparsecs, that includes both superclusters and cosmic voids. Do not think of the cosmic voids as being empty due to some repulsive anti-gravity. Dark energy does not repel in that way. The slight underdensities of dark matter expanded faster than the universe's average expansion, which further reduced their density. Cosmic voids also lost matter to the gravitational attraction of nearby dark matter overdensities. Here is a distant image of the cosmic web. Clusters and superclusters seem to have collected into long filaments, shown in green, bordering the cosmic voids, shown in dark blue, in this artist's visualization. Here is the result of a simulation of the structure formation of the galaxy filaments and cosmic voids. Nearly every non-dwarf galaxy is believed to have, at its core, a rotating supermassive black hole of mass several hundred thousand to billions of solar masses. Cosmologists do not know when supermassive black hole precursors initially formed, but some may have existed when the first stars were formed, not from the subsequent merger of massive stars. I wonder if perhaps dark matter had a component that was clumpy at early times and formed the seeds of the supermassive black holes. You will sometimes see an article discussing primordial black holes, or even whether supermassive black holes were an artifact from a prior universe that survived our Big Bang intact, though there is no evidence for this. It seems to me that the number density of such artifacts would have become extremely diluted by cosmic inflation, if cosmic inflation is true. Gas and shredded stars spiraling toward the supermassive black hole event horizon, an accretion disk, heats up and high-energy particles escape in two jets in opposite directions. This is the jet in one direction. Early in the life of a galaxy, the jets can be brighter than the stellar core of the galaxy. These cases are called quasars, or active galactic nuclei, AGNs. Early quasars were so bright that they are visible from greater distances than ordinary quiet galaxies. Astronomers first detected quasars in the 1950s.